brain freeze.
So let's get started. It's my pleasure to introduce Swabha, Assistant Professor of Computer Science and Co-Associate Director of the Center for AI and Society at USC. Her primary research interests are the evaluation of generative models of language, understanding the behavior of language models, and designing language technologies for societal good. At USC, Swabha leads the Data Interpretability, Language, and Learning Lab. Her work has been recognized with outstanding paper awards at top venues. And without further ado, please join me in welcoming Swabha.
Thank you very much for having me. Today, I will use this opportunity to talk about some work in my lab, unified by this theme of small samples, big reveal, where we will use very limited resources or very little data to still tell us something about these large language models. So why should we care about this kind of research? So as you all know, we live in a wonderful, wonderful world with large language models. So the most famous, most popular, most used language models are the ones that are very large. I don't have logos for all the excellent work being done in China for language models. Where does academic research fit in? If you look at these large language models and the contribution that you have from universities seem kind of tiny. So what can we do in this era of large language models, especially given these challenges that these are not only large but also closed source? So studying them as a scientific entity becomes very challenging. They're also private. So how can we do creative research in this era? So that is something I constantly think about. So my research tries to look at three different problems in this era of language models. The first one is understanding language models based on their test time behavior. So this is not just the language outputs that you get, but also the representations and the geometrical understanding that we have of these transformer models. So you can put some of this work in this language model inference, evaluation, and interpretability umbrella. The second thread of my research is developing algorithms that can improve language model safety and accountability. So here we look at how do we process rewards, how do we build safeguards for language models, how do we design attacks and protection against those attacks for language models, and how can we improve accountability by introducing some kind of watermarks into language models. And the final thread of my research is designing safe and private language models, which are amenable to human AI collaboration, so we can use them in high stakes applications where you might not necessarily want to send your data to private closed source models. This might be very sensitive data that you want to keep as locally as possible. Here I look at some applications in personalization, AI and society. So this is kind of related to the Center for AI and Society that I co-lead. And I know there are folks here who are interested in that line of research. So happy to talk about that. Outside of this talk, I won't be talking about that last thread at all. I will be only focused on the first two. So today's talk will focus on the first two threads of my research. So in the first part of the talk, there are two parts to this talk. We will discuss something called microbenchmarks, which are a new way in which these language models are being evaluated, and how this evaluation can reveal a lot about the language models, as well as our training data with very few samples. In the second part of this talk, I will talk about this new problem of language model inversion, where we take the outputs of a language model and try to infer what was the input of the language model, what was part of the hidden prompt, and what does that say about the language model. The cool thing about both these projects that I will be talking about are is that they were used with very minimal access to GPUs. Obviously, there were some GPUs involved, but nothing crazy. We didn't have to seek out external, support for running large-scale experiments. Some of the projects in my lab do, but for these two projects, we didn't have to do anything outside of whatever we have at USC. So before I get into the topics, I want to tell you about a couple of caveats. So evaluation is a very big goal. There is no single project or single effort that can fully address all of language model evaluation. And so we have to do, make small innovations, make small changes to how we do evaluation better, more responsibly, and no one benchmark, no matter how large it is, can do all of evaluation. No one method for evaluation can do it all. The same thing with accountability. We will be talking about one aspect of accountability, and all of these are stepping stones towards better language model accountability in general. So we will be talking about hidden designs and private models, but there are other ways in which accountability can be improved. And before I move ahead, also one caveat, I'm telling you a lot about how little GPUs we used, etc. This does not mean that we at USC do not have any GPUs. It's not anything like super impressive, unfortunately, but it's not, it's not so embarrassing that we cannot do any research. We have a reasonable cluster for NLP. Depending on who you ask, it might be a small cluster or a big cluster, but you're getting some A100s shipped in this week, and so it's a continuously growing resource that we have at USC. So we are not exactly resource poor, but compared to a big industry lab, it's probably nothing. Anyway, with those caveats, let's proceed. So the first project I want to talk to you about is microbenchmarks for language models. This is work that was just recently accepted at iClear 2026 and was led by my former postdoc, Greg Yanni. All right. So what are microbenchmarks? Why do we need them? So as you all know, a big cost with language models happens at inference time. Training is obviously expensive, but once you've trained the model, it's done. But you do a lot of inference with the model, and that is expensive. And the way we evaluate language models is we run a lot of inference on language models. So we need to do some kind of rapid evaluation during development, right? So the purpose behind these microbenchmarks is that you can build a very small benchmark. You can sample the large benchmark into a very small microbenchmark, which contains like a very small fraction of examples, sometimes even less than 100 examples, to make this evaluation more rapid. So this is the idea behind microbenchmarks. And the goal is that models with similar accuracies on benchmarks should have, or a model should, the performance of models on microbenchmarks should reflect the performance on the full benchmarks. That's the goal. So how do you select examples in a way that these two performances are correlated? One thing that might be obvious to you as I talk about sampling less than 100 examples from these benchmarks is that you are talking about some kind of a loss of statistical power. And this happens, but this is a trade-off that language model developers are okay with because inference costs are so high. So people are okay with losing that statistical power, that statistical reliability, and using microbenchmarks still in the process of model development. Okay, so how do people develop these microbenchmarks? So one simple approach is random selection. You randomly select k examples uniformly at random from the full benchmark. You can do something more elegant by looking at different sets of examples. Maybe these sets are defined by different subtasks in the benchmark, and you can select k examples from each subtask, right? Or you could cluster examples based on the model confidence, some kind of aggregate model confidence based on a selection of source models that you have that you won't be evaluating on, and you can select examples from each cluster. Some more sophisticated methods have also been proposed. For instance, tiny benchmark is a micro benchmark that you get from training an item response theory model for predicting how well the model will do on any particular instance. So you build an instance-specific simple linear model that will predict how well any model will do on that instance. So that's one of the micro benchmarks we consider. And perhaps the most sophisticated, although not that much more sophisticated, is anchor points, which has a very similar idea as the stratified sampling, although the way they create these clusters is by looking at some kind of correlation between examples based on the confidence of a certain set of source models on these examples. So we cluster examples based on some model confidence and then pick the medioids of those clusters. So that's what Anchor Points does, and this research came out a couple of years ago. To the best of our knowledge, people do use similar methods for rapid evaluation during model development. Okay, so the question, yes.
This was the setup of the benchmark itself. It's just like a static data set which has been sampled and now it's being used for evaluations, or the other way around also. That this is also a dynamic process where you can have the different sets which just be giving you the optimal micro benchmarking computation that you want. You can just sample different of them at different times, and that can give you better statistical data.
Yeah, so great question. To the best of our knowledge, it is a static process. Like you do this once and you use that multiple times, but what you're saying is also perfectly possible. Although, yeah, so the thing that would be changing is like the pool you're sampling from, which, yeah, maybe as maybe more evaluation data becomes available, you can sample from that larger pool, but not with the static benchmarks that we commonly use for model development. Yeah. Okay, so the question that we are interested in is evaluating how good are these microbenchmarks? How reliably do microbenchmarks echo the model performance on the full benchmarks, right? So here, give me a second now. All right, this is much better. Yeah, so this is a kind of a meta evaluation because the evaluation is being done on the micro benchmark, and we want to evaluate that evaluation set. So existing methods look at things like the mean estimation error, which is model specific. How far is the performance on the full model from the performance on the micro benchmark? Very simple, but this only considers a single model, and then it takes an aggregate across individual models. You could also look at aggregate rankings. So between the full benchmark and the micro benchmark for all models that are involved. But this also tends to be a little coarse. It does not reveal, for instance, which model comparisons are preserved. It considers any model comparisons to be equally important, which is not really the case. And it is not really the case because, going back to the goal of why we need these micro benchmarks is to enable rapid and reliable model development during training. So that means we are doing a lot of comparison of checkpoints. And as you know, like checkpoints that are close by tend to have similar performance. So what we need is some way to reliably compare these different checkpoints, which might have very similar performance. So what we care about are these pairwise model rankings, especially of model pairs, which are very similar to each other, right? So the idea here, again, is that the model, if model M1 outperforms M2 on the full benchmark, does it also outperform M2 on the micro benchmark? So that is the pairwise idea that we care about, right? So, and in aggregate, we'll be looking at all possible pairs, but this is the idea behind our evaluation, which is not really captured in the mean estimation error or Kendall tau. So again, the key intuition is that if there are two models that have very different performance, those might be easier to tell apart, but if they're very similar to each other, it can be a little tricky to tell which is better. So the goodness of the micro benchmark should be a function of the performance difference of any two models that we are using to evaluate this micro benchmark. So we will be using this delta between the performance of M1 and M2 of two models on different sets, full versus micro benchmark. So the main thing we will be looking at is this agreement. If two models have a certain ordering on the full benchmark, do they have the same ordering on the micro benchmark? We don't care about the performance difference as of now. We just look at different buckets of performance differences. That is what B tells you. And we are making this agreement a function of that B, that bucket of performance. And here we experiment with buckets of different granularities, and we can get rid of the buckets altogether, but let's just consider this right now. And we're looking at the probability that the micro benchmark will have the same ordering for the models for that particular bucket. So just to give you a visual idea what this looks like. So let's say we have a micro benchmark that has only 10 examples. So it has sampled only 10 examples from, this is MMLU Pro, I believe. So that's just 0.2% of the entire MMLU Pro. And we are looking on the x-axis at the accuracy difference between models on the full benchmark. And on the y-axis, we are plotting this agreement, which is just the probability of that ranking being consistent. And here we are comparing two different micro-benchmarking methods. Blue is random, where we are randomly selecting, uniformly at random, we are selecting examples. So if we look at this 80% probability line, what we are seeing here is that when models are around 4 points away from each other, anchor points can reliably capture these rankings between M1 and M2. So 80% of the time, microbenchmarks that are created using anchor points can reliably capture that comparison. Whereas for random selection, that is only possible when the models are nearly 20 points apart in performance. So that's a big difference. We want this agreement to be very high for as little of an accuracy difference as possible. So ideally, we want everything to be in this top left corner, but looks like there is a big difference between how anchor points does it versus how um, random selection does it. Any questions so far? Yeah.
One, you mentioned this frequently, maybe just I wanted to check if, like, why can't you just use like a correlation of it kind of thing with the actual performance of?
Yeah, so correlation doesn't tell you anything about which models we're comparing. So remember, we care about models that are more close to each other. The correlation will just give you an entire ranked list of models. That's why it's a little coarse.
To the bucket B that we have, are we doing it for all pairwise models in that bucket or like?
Yeah, exactly. So that's a simplifying way in which we want to categorize everything. But you can get rid of the buckets altogether and just look at every pair and still get the same similar kind of a metric. Yeah. Other questions? Okay, so remember, this is just for 10 examples. 10 examples is very few. What happens if we look at, and yeah, here we care about this line, which is 80% or greater agreement, which happens to be 80% is something we use also in statistical power, etc. So it's a threshold we choose. We also have experiments showing like, if you change that threshold, what happens? And our results are more or less, intuitive. But let's just consider this 80% for now. But what if we increase this to now 50 examples? Here we see that the two lines are getting closer to each other. So that means random is starting to get a similar performance as anchor points. And when we select something like 1,000 examples, they're fairly the same, more or less. Anchor points is actually a little worse now than random selection. So the more examples we select, it looks like random can give a better ordering between model pairs, more reliable, more consistent than anchor points, which tends to work better for smaller example sizes. Okay, so that's a somewhat surprising finding. We thought if anchor points is better, it should continue to be better, but at some point, random starts outperforming. Yes.
Looks like, fairly similar, or like any sort of improvements to see much faster information transfers random points, that's obviously improvements. Could you come on why the anchor points are fairly similar plus the others?
Yeah, so I wouldn't say they look fairly similar. It's moving more and more to this left-hand corner. And it's, yeah, but the bigger question is that, like, why does anchor points work pretty much the same at these different levels of examples? I believe it is because, it is capturing some kind of a representative subsample of the entire benchmark. There are some reasons why it does it, because anchor points depends on the probability of the model or the confidence of the model in the correct class. And that is something that makes it only adjustable or applicable to classification benchmarks. And that's a very strong signal, the probability of the correct class, which random selection obviously doesn't have. So that could be a very important signal that anchor points has. But that also makes it not very generalizable to, generation benchmarks, for instance. So that's it does work very well with very few instances, but still, like, models need to be 4 points apart, which is a big difference for checkpoints even. Okay, so if we look at what the high-level findings are at this stage, we see that anchor points cannot consistently, so sorry, the colors are a little off here, but if you consider this line at 4, you can see that anchor points cannot distinguish between models which are 4 points performance apart from each other, because this line is intersecting at this 80% line only when the accuracy is 4 points apart. So after this, anchor points is great. Other approaches are not even close till 20 points. And this is with 10 examples. But when we are selecting 500 examples, other approaches are actually doing much better than anchor points, which is interesting. And again, no method can reliably rank models that differ by fewer than 2 points of performance. So if checkpoints are very close to each other, microbenchmarks can actually mislead you if you are using them. So that's a risk you have to be willing to take if you consider very tiny benchmarks. But if you consider something like 500 examples, then models that are maybe even like 1.5 points in performance, or 1 point in performance apart, you can reliably compare them. So using 500 examples, good idea. So we take this. So instead of looking at all these different accuracy differences, we wanted to have a metric that summarizes everything. So again, we care about the performance difference. We care about this 80% or higher reliability. And we want to consider the minimum performance difference at which that micro benchmark becomes reliable. Yes.
Yeah, I wonder, maybe you will be talking about this, but have you been looking for the scaling effect of number of examples? In the sense that because you care about this micro benchmark, or a small sample. But I think usually you have a 10 example and then you jump to the previous page 500. Here you have 50, but it's 1050 and then the 1,000. You see some points that they can.
Yeah, just I'm going to show that right after this, yes. But we do consider that, yes. So we consider this metric that we call MDAD. I may or may not have been involved in the naming of this method, so don't ask me questions. But so what this captures is that minimum accuracy difference, and for this bucket that we computed the agreement for, you just take the centroid of that bucket for simplicity, and that tells you at what minimum accuracy difference do these comparisons become more reliable, right? So to answer Nanyan's question, here is what we see. Like on the x-axis, we are varying the number of examples, and on the y-axis, we have this MDAT metric. The lower, the better. The lower tells you that at a very small difference in accuracy, these performance differences are meaningful, have that 80% or higher reliability. So here we can see that anchor points is much better at this reliable comparison till you select around 250 examples, after which random becomes much more reliable. So there is something of a smooth tendency here, but it obviously depends on the method that you are using. So these are all curves for MMLU Pro, and those are the numbers we get. Okay, so at a very high level, what do we learn? So when we are selecting less than 100 examples, all methods struggle more or less. Anchor points does the best for distinguishing models out of the methods that we evaluated. But when we care about more examples, random sampling can distinguish these methods as well as other methods. So, you know, and more than 250 examples also gives you higher statistical power. So if you don't want to go into this problem of, doing this anchor point based selection, you're better off just taking something like 250 examples and randomly sampling those examples from the full benchmark to build your micro benchmark. And you should be, you get some nice guarantees, and you are also saving yourself a lot of effort. All right, so that's where I will stop. There are more analytical experiments in our paper, but what we learned here is that microbenchmarks contain a number of samples. They still tell us a lot about the data. They still tell us a lot about the models that we are comparing. Too few samples where these microbenchmarks even start. Random selection should never be taken out of question. Random selection always helps. So that's a very nice finding. All of these experiments we ran. Okay, so we had access to the model predictions on all these benchmarks for a suite of models, which thankfully the anchor points folks released. So with access to that, we were able to run all of these experiments on my postdoc's MacBook. So that was very cool. When does that happen ever? But yeah, while everyone was struggling with conference deadlines and GPU rush, my postdoc was running experiments very quickly. So that was very nice. All right, any questions? Okay, moving on. Yes.
What's the dot? The paper the dot in which was not
So it can be any task really. So most of the prior work has looked at tasks like MMLU Pro, Big Bench Hard, so classification benchmarks, and anchor points can only be built for those benchmarks. But our approach is general enough that it can evaluate any micro benchmark, no matter how it has been built, as long as you are reporting some kind of performance difference. But most people do these evaluations on classification benchmarks. Mm-hmm.
I have some question around the sort of the use case, because I think you start by saying inference is costly, so you want smaller benchmark. Is that another possibility is that here a lot of your things assume you already have a big set of annotated data, and then you sample from it, which means the annotation is already done. But another use case would be annotation is very expensive, and you choose data to annotate so that you'll have your micro benchmark to be small to begin with, but still are very powerful to distinguish model. I wonder whether anything you're doing here will be applicable to that setup. It's like assume it's more like active learning, but not active testing. Which means you're not learning, but you actively select examples to annotate so that you can use a minimum amount of data.
Yeah, so that's a wonderful question, and the answer is yes. So remember this micro benchmarks is something that people have done before. Our approach only cares about these performance differences, which is very easy to compute in these active testing settings, right? Like you are actively sampling examples, or you're synthesizing examples even, on which you maybe are doing some kind of LLM judge evaluation. So as long as you have those kind of performance differences between, something that is an existing framework and what you are creating, you should be able to use our method for figuring out if that sample that you're creating is good enough. So we are not yeah, like as long as you provide like a small set and you have some kind of a reference, you can apply our method. Our work is not advocating for a certain kind of micro benchmark, although my student Shahzaid, who's the second author on this work, is looking at a way in which we can use our method to sample better. But we haven't still considered these kind of active testing setups, which are more generative. It is still like a sampling setup, but that's food for thought. I have to think about it. Yeah. Thanks. Yeah.
Maybe one other thing I'm thinking, I don't know if people already use it, but more for cases where we need subjective evaluation as like you have to do objective things. Do you think, like I believe it should, but have people tried, and do you think this will also work in those setups where instead of evaluating on like hundreds of like getting some subjective evaluation from humans as well on some hundred pairs of data, and just do a 10 pairs get an idea?
Yeah. So even human evaluation, right? Like it is picking one over other.
Yeah.
So if you are aware of like subjective evals, which just pick like some kind of set over the all possible sets, I wouldn't be able to answer that, but to the best of my knowledge, I don't see that kind of evaluation happening. But even pairwise evaluations are kind of you are picking like one over the other, and as long as there are like limited number of choices and you're picking one over another, it should be possible to do our thing. Yeah, good question. Okay, so moving on to the second part of my talk, we'll talk about a very different application where we are looking at inverting a language model. And the reason why we will be doing something like this is to understand something about the language model that we may not originally know, or to see like what our outputs, language model outputs, really tell about the language model. So, okay, so as a recap, I'm sure everyone here knows this. This is what, at a very high level, a language model does. You have some input. All our language models are more or less transformer models, all the very successful ones at the very least. And once we have this transformer model, we get some kind of embedding out of it, which is this hidden state. We have that last layer, which is this unembedding matrix called W. We do this mat mul at this stage. Then we pass everything, the logics that we get, which will be of the size of the vocabulary of the language model. We pass that through a softmax function to get probabilities, and the probabilities are what we sample our next token from. So that happens in every language model, more or less. So what people really think about when they think about the language model outputs is just the tokens that come out of it. But we all know that actually what comes out of a language model is that probability vector or this logic vector. And then you can do some kind of sampling on top of that to get the next tokens, right? So language model outputs go beyond that, beyond just tokens. And here what we leveraged is that these output probabilities, they tend to hold a lot of information about the language models. Here's those probabilities, which we don't take as seriously. We usually truncate most of them, we throw them out, and we only care about the top few probabilities, but actually that entire vector has a lot of information. And we will be using that information from that entire probability vector or that entire logic vector to reveal something about the input. So if your input is hidden, if you use a hidden input that gives some kind of output from a language model, we can use the output of the language model to tell you what that hidden input was. And that's pretty cool. Uh, if I can say so myself, although I did not come up with this problem was actually something that was studied by folks from Cornell, who looked at this language model inversion problem, taking the probabilities and predicting the input. And why is this a problem that we should care about? Lots of language model providers may have hidden inputs or system prompts that contain a lot of information about, what to do, what not to do in the language model generation in its output. That might be interesting to look at, and because everything is private, there might be malicious attackers who might try to get that information. So one way in which this information can be obtained is by looking at an inversion model like this. And if we can, make this inversion model better, we can also come up with better protections against that inversion problem. Okay, so this is the problem. How do you recover hidden prompts using the language model outputs? So this can either be done on a purely text level. You just look at the text output, usually the greedy output, and you try to predict the input, or you look at the log probs or the probabilities, logics, any of these things, and try to predict the text input. Okay, so this may seem like, at least the first time I saw this problem, this seemed like very magical to me that this is even possible. But turns out you can do this using a T5 model, just a sequence to sequence model, which you feed in those vectors to, those probability vectors to, and you can train the model to spit out text from those vectors. This is very cool. The first time I saw this, my brain was broken a little bit because, we train these seek-to-seek models to handle text, but they can handle anything. They can handle random vectors of real numbers, which is crazy. Anyway, so this is the language model inversion architecture. So you have some kind of hidden prompt which goes through the language model, which gives you log probs. Let's say we have log probs across t time steps. We take those log probs only, pass them through an inverter, and recover the prompt that was originally sent to the model. Okay, so logic to text was the original model that I talked about that introduced this problem and tried to do it using a T5 model. So one practical problem, the main practical problem here is that these probability vectors are very long because the model vocabulary is hundreds of thousands of tokens. And that usually doesn't fit into the input. So what they did is that they broke the vectors into 3 different parts, as I've shown here, but actually ceiling of V by D, different parts, and sent that to the inverter, and the inverter was supposed to return the hidden prompt. Okay, so what we did is we figured out a way in which we can compress all these probability vectors into more compact representations without losing any information. So we figured out a way in which we can losslessly compress these probability vectors such that our inversion problem improves dramatically. So that's what we did in this work. We took these log prob vectors, we compressed them, and this is a linear compression that exists. And we got these d-dimensional vectors, and this d happens to be the same as the embedding size of our inverter. And we send this to our inverter, and we name our model pills. Again, not involved in naming the model prompt inversion from log prob sequences, but I can promise you this was the best abbreviation we could come up with. Yeah, my lab needs to do a little more effort into naming things, but yeah. So this is a way in which we can compress these vectors such that the inversion problem can be simpler. Yes.
One problem is, I think, do you assume access to the user prompt that you're using, or is that also something that you're trying to predict?
Yeah, so yeah, this is another thing that was also surprising to me. Apparently, there are data sets that collect these user prompts and the output vectors. So we use these data sets, but I mean, in principle, you can create a data set of that kind very easily. If you use some kind of an API protected model, you won't have access to the system prompt, but you still have access to the user prompt, the task prompt, which gives you some output. Yeah.
So the task is still to recover the whole system plus user prompt. Ideally, we don't know the system prompt.
Yeah. So most of the data sets are only considering the user prompts. There are some data sets that have both system and user prompt. System prompt is a little harder because it's deeper down.
I wonder, like, if you just use the like decoder only, like, why need to use the system?
Oh,
Like, you could also just do those,
In-
not like the embedding or something.
into the embedding. That's what I thought was the most reasonable thing to do because these are, but for some reason, that's not something that prior work has done. And my guess is that you still need to adapt a decoder only model in some ways in which it can handle these output probability vectors, because there's got to be some kind of a distribution shift. So the most intuitive thing to me was that, like, you still take a seek-to-seek model, but instead of feeding in these probability vectors directly, you would feed it into the embedding layer. But turns out you don't even need to do that. It's an open question whether we can do this by just changing the embeddings. Maybe there's a distribution shift that happens. I don't know the answer to that. Yeah. Okay, so the next question is, how do we do this compression? So the reason we can do this compression is because remember in that first figure we had language model hidden outputs, which are a d-dimensional vector, which we project to this v-dimensional, either probability vector or the logit vector in, probability space or real space. And we take that as the input to the inverter. Turns out, because we do this big projection, the final layer that we have is low rank, because that unembedding matrix, the dimension V is much, much larger than D. So that means we can losslessly compress the entire full next token probability distribution into just D dimensions, which is what the model knows how to process. And this lossless compression that we are able to do is preserving all the important information in that large probability vector, and that makes these outputs very compressible. So this is another way in which we are saying that you actually don't need all the V dimensions. The most important dimensions are like a subset D dimensions. And remember, D is something like a few thousands maybe, and V is hundreds of thousands. So we are getting like 2 orders of magnitude compression, which is possible. So this allows more output information to be used for for inversion. So you can pack in much more input into this inverter. So to give you a little more detail about this lossless compression, so we take this hidden state that is, goes through this unembedding matrix multiplication to give you logits, which goes through some softmax operation to give you probabilities. Now we can take those probabilities and expand them back into real space with something called this additive log ratio transform. It's a very simple transformation that gives you reals from probabilities. And from that vector, we can just select a subset of D dimensions from that vector to get the inverter input. So which D dimensions? Turns out you can randomly select D dimensions, and that seems to work pretty well. We tried things like the first D dimensions. That is not good because there is some dependence between those dimensions. But as long as we select D, so we ideally need D+1 because D is the hidden size. So any D+1 that we select should have, in theory, enough information so we can, it can be a lossless compression. And so this entire transformation is a linear transformation from H to this inverter input D. It's not exact. There will be some kind of, noising that'll happen, but for most part, it is good enough to be an approximation of the hidden state H. So language model output probabilities are linear projections of that final hidden state. And we have a nice little proof in the paper that tells you why this linear transformation is possible. It involves showing some properties about the softmax function, which are very interesting. If you're interested, please take a look. And it is possible to recover the hidden state up to a linear transformation, which is very cool. Ooh, I'm almost at the end of time. Is that right? Okay, I'll just quickly go over some results. So once we are able to do this kind of transformation, what do we see? So this is a this diagram looks more complicated than it actually is. So on the y-axis, I am showing you the top output token and the generation step. So this is from the actual language model. And on the x-axis, I'm showing you the prompt tokens, which is the hidden prompt we are trying to recover. So here the idea is that as you're seeing each output token, but really we are looking at the entire probability vector, what are you able to predict about the hidden prompt? And I wish this was not grayscale because it doesn't render well at all. But okay, we'll look at the actual outputs that our inverter model tells, which is what I've shown on the right-hand side. So when it sees that first position, it tells me tell me about a time you was to, when the actual real prompt was tell me about a time when you felt afraid. And you can read the outputs with many different generation steps. Around this step, you can see that we recovered a paraphrase of the original hidden prompt, which is very impressive. And if we keep on going deeper and deeper into our input, deeper and deeper into our output, we can recover this hidden input almost exactly or exactly. So that's very cool. We can do this very, very easily with just 22 inputs, which fits into a T5 architecture. There are some prompts which are easier to invert than others. For example, reverse a string, and it gives you the string, so you can reverse it very easily. Remember, we are not looking at any of the output tokens. We're only looking at the probability vectors, and based on the probability vectors, we are able to recover the actual hidden prompt. Okay, I'll skip over this part, but it's actually very impressive. We get big improvements on performance compared to the baselines because we are able to pack in so much information. And this is true both in and out of domain. So these kinds of improvements are really fun to see in today's day and age, where we are going from the 70s to almost the 90s. As your architecture gets more complicated, it becomes harder to do this kind of inversion problem, but you're still able to do much better than we were able to previously with previous models. there are some kind of challenges we see to other encoders. So for instance, if we trained our model using Llama 2 13B, we cannot just generalize to Mistral 7B that easily. There is some extension possible, but it still seems to be hard. System prompts tend to be the hardest because system prompts are much deeper down. So recovering system prompts is still a little bit of a challenge, and we don't get very high numbers, although we do much better than a text-only inverter in getting this. So in summary, we were able to learn a lot of things about these language models without necessarily having access to tons and tons of resources. We were just training these T5 models. There were some memory requirements, but not so much that this research was prohibitive. I had some backup slides on other work that is done in our lab on, like, again, building some kind of signatures for language models that can tell us something about the language models without access to a ton of information, and how that can be used in like a cryptographic setup, a very lightweight cryptographic setup to enforce accountability. I won't go into that. We also have work on training data watermarks, where you insert a watermark into whatever data you think your language model might pick up, and you can still verify whether the language model actually picked up your data, which is, again, very few insertions are needed for a language model to actually reveal that this happened. So around 200 or so insertions into your data can reveal this. So that's another way in which you can hold language model providers accountable. So in summary, we showed that reliable evaluation can be done with fewer instances, and we can learn a lot of things. We can ensure some kind of accountability for language models with very few instances. So in no way am I saying that, do not do research that involves scaling. Scale does matter. And all these problems that I showed you today, if we scale it up, it's most likely going to work much better. So it's not that scale does not matter. However, these are important problems that we can work on at a very small scale and show that this kind of work is possible. And the hope is that, those with resources can pick up this kind of work and maybe scale it up to have like practical utility. So research done at smaller scale still matters. And hopefully this is a good message for, folks like yourselves in academia. You can still make meaningful discoveries. You can do very creative research with powerful language models. And I'll stop there. These are the folks who led the work I presented. And thank you. That's my lab. Any questions for me?
I have some questions about the article that you mentioned, on the inverter of the two sets of quick questions. Do you have some comments on how does it scale with the length of the prompt that you're trying to fill?
Yeah, the longer the length, the harder it is to invert. So that's why we were struggling with the system prompt.
The other thing is, do you assume access to the logics and the price of itself, or do you work with the probabilities itself?
It doesn't matter. Either is equivalent, because logics and probabilities is just a softmax function, which does not cause any problems.
My question there was mainly if there's some temperature, based softmax that is applied and it makes a distribution skewed, then the probabilities.
Yeah, so if it is skewed in a way that is still like some kind of a linear transformation, we're fine.
Yeah.
But if it is like random noise, then it might be a problem. So that is actually a good defense against this attack.
Yeah, that's what I was thinking about.
Yes. So if you want to build a defense against this attack and you're a language model provider, it's in your interest to noise the logic of probability from.
Thank you so much.
Other questions? Okay, thank you. Thank you.